Welcome back to another Gungahlin College Maths Applications online lecture. So today we're going to start an entirely new topic. We're going to start talking about sequences and series. So if you like puzzles, hopefully you'll like sequences and series. But the topic of this lecture is actually going to be just sequences. So really today we're just going to get started with the idea of what a sequence is. So what is a sequence? Well, it's really just an ordered list of numbers. So really any ordered list of numbers makes a sequence. So let's give a few different examples. So the first one is really the simplest one that I can think of. So it's 1, 2, 3, 4, 5, and so on and so forth, right? So this is the sequence where basically every time we add 1, right? So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, etc. So the next number in the series would be 6, and so on and so forth. So that's one example of a sequence. Another example might be, say, even numbers. So 2, 4, 6, 8, 10, right? And that could keep going, so the next number would be 12, and so on. Another example might be this one here. 1, 2, 3, 5, 8, 13. This one also has a pattern, and that pattern is that from 3 and on, all of the numbers are the previous two numbers added together. So 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 3, 13 is 8 plus 5, so the next number would be 13 plus 8 is 21, and so on and so forth. Okay, now here's another example of a sequence. 34.68, 34.33, 34.62, 34.37, and so on and so forth. Now this is just to show you that not all sequences have a nice easy pattern, right? So this one here is you couldn't predict what the next term would be. This is actually the list of closing prices for BHP Billiton. So if you could predict what the next number in this sequence is, what the closing price would be on the following day, you'd be able to make a lot of money. It's not actually predictable. Okay, so those are just a few different examples of things that are sequences. So now I just want to introduce you to a little bit of notation. So given a sequence, given the sequence, let's see, this one here, number 3, 1, 2, 3, 5, 8, 13. If we call this sequence T, then we can refer to any one of the numbers in that sequence, and this could keep going on, by T subscript the term that we're interested in. So for instance, T subscript 3, so T little 3, would be equal to 3, because that's the third term in the sequence, right? T5 would be 1, 2, 3, 4, the fifth term is 8, so T5 would be 8. And then in general, right, we could say the nth term was the nth term. Okay, so this would, Tn would be the nth term in the series. Okay, so that's just a little bit of notation to help us out with what will follow. Okay, so there are a number for the sequences where we have a predictable pattern, right? So for like number 1, number 2, and number 3, not so much for 4, but for 1, 2, and 3, there are different ways of defining the series, right? So basically like a rule that gives you the pattern that tells you what the series is going to be. So one of these ways is called a functional definition. So don't get too worried about the name. We'll talk about what it means. So a functional definition of a series. So let's just start with an example to be really clear. So let's go back to that really simple example, 1, 2, 3, 4, 5. Okay, so we could give this what we would call a functional definition. And that functional definition would be this, that the nth term in the sequence is equal to n, for n is equal to 1, 2, 3. So what exactly does this mean? So that means the first term is just 1, the second term is 2, the third term, t3, is 3, etc., right? So now this seems like a fairly silly way of defining this sequence. It seems like a lot of stuff to write down for such a really simple one, and that's really true. However, there are more complicated functional definitions that you can give where it would be quite tricky to do without the functional definition. So let's do an example like that one. So e.g. So here I'll just give the definition, and then we can write out what the series would be from that. So if I gave you the definition for a series, Tn is equal to n squared minus 3, what would that series look like? Okay, well, T1 is equal to, well, what's T1 equal to? So when n is equal to 1, all we need to do is substitute this 1 in to this equation here. So T1 is 1 squared, right, when n is equal to 1, minus 3. 1 squared minus 3 is 1 minus 3, which is equal to negative 2. So the second term in the series then, T2 is, again, you just substitute this 2 in to this equation here, so that'll give you 2 squared minus 3 is equal to 4 minus 3, which is equal to 1. T3 would be 3 squared minus 3. So hopefully you guys are getting this by now. 9 minus 3, which is equal to 6. T4 be 4 squared minus 3, 16 minus 3, which is 13. So our series, our sequence would look like minus 2, 1, 6, 13. Right? And here it would be hard to guess what this was just from writing the sequence down like this, but if somebody gave you this definition up here, right, Tn is equal to n squared minus 3, it would be pretty easy to figure out what the next term was going to be. Okay, so that's an example of a functional definition. So some sequences, on the other hand, have a definite pattern to them. So the one that I'm thinking of now is this one up here, right? We said that 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, etc. So there's a nice pattern there, but it would be really hard to write down a functional definition, right? One like this for that. But there is, fortunately, another way of defining what a sequence is, and that's called an iterative definition. So what exactly does this mean? Let's start again with a really simple example, because I think that's the best way to help you guys understand. So let's start again with that really simple example, 1, 2, 3, 4, 5, right, which seems to be my favorite sequence today. So I could give you an iterative definition. So iterative definition means that for every member of this sequence, we define it in terms of the previous one, or a combination of previous terms. So for instance, right, I could say that here T2 is equal to T1 plus 1, right, because 2 is equal to 1 plus 1. T3 is equal to the previous one, right, 2 plus 1, so that would be T2 plus 1. T4 is T3 plus 1, etc., 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 right? So you can see a pattern here. And we could say in general, right, that T of n plus 1 is equal to Tn plus 1. So basically what this means is the next member of the sequence is always the previous one, plus 1, right? So again, this seems like a really long-winded, sort of silly way of trying to define the sequence, but it's one way that we could do it, right? This isn't actually enough information, right? Because you could say, let's say you started your sequence out at tn is equal to 3, right? Then your sequence would start at 3 and be 4 or 5, and you wouldn't ever have the 1 and 2 there. So another thing you'd have to say is what t1 is. So t1 here is equal to 1. Okay, so rather than get bogged down here, let's try to do another example. Let's try to do that one example where I said there wasn't a nice way of giving you a functional definition. So what I'm going to do is instead write down the iterative definition, and then we can reconstruct what the series would be. So I'm going to say that for this one, the tn plus 2 term is equal to the tn plus 1, so the one before it, plus the one before that, tn. And furthermore, I'm going to start this out with tn is equal to 1, not tn. t1 is equal to 1, and t2 is equal to 2, right? So the sequence is going to start with 1, 2, and then we're going to see what we get from there. Okay, so let's now look at the n equal 1 case of this description. For n is equal to 1, t of n plus 2, n plus 2 is 3, so that's t3 is equal to, what's it equal to? tn plus 1 is t1 plus 1 is 2, plus t1, right? And we just said what these things are. t1 is 1, t2 is 2, so this is 2 plus 1 is equal to 3. Okay, so for the n equal to 2 case, right, now tn plus 2 is t2 plus 2, which is t4, is equal to tn plus 1, which is t3, plus tn is t2. So this is equal to, we just worked out what t3 is, it's there, right? So that's 3, t3 is 3, plus t2, we set up here, was 2, so this whole thing is equal to 5. So t4 is equal to 5. n equal 3, when n is equal to 3, then we're thinking about the t5 term, right? tn plus 2 is t3 plus 2 is 5. tn plus 1 is t3 plus 1, which is t4, plus tn is t3. We just worked out what t4 is. That's 5. Plus t3 we worked out before is 3, is equal to 8. So we could keep going on and on, but you guys should hopefully see by now that this is that same series that we talked about at the very beginning. It's 1, 2, 3, 5, 8. Now if that was confusing, well hopefully it's not, because you'll have to get used to doing this sort of thing with iterative definition, but at every point, right, so you start with this one here. This one here we said was the one before that plus the one before that. This one here is the one before that plus the one before that. So it's always basically the two preceding numbers added together. So the next number would be 13, etc., etc., etc. And all this relationship up here is saying is exactly that. Okay, so that's an iterative definition. And that's all for this video, but in the next video we'll talk about something called the logistic equation. Alright, see you soon.